In this video, I'm going to talk about open sets and closed sets in the Euclidean space Rn. Let me start with the definition of addition, scalar multiplication, and the Euclidean norm in Rn. We denote by Rn the set of all n tuples of real numbers. In Rn, we can add two elements by adding their corresponding components. We can multiply a real number lambda with an element in Rn by multiplying lambda with their corresponding components. In Rn, the Euclidean norm of an element x is computed by the square root of the sum of the squared components. Next, I am going to talk about the definition of an open bond in the Euclidean space Rn. Let C be an element of Rn and let R be a positive real number. The open ball centered at C with radius R is defined as follows. The open ball with center at C and radius R is the set of all elements of Rn such that the Euclidean norm of x minus C is strictly less than R. Here is an example of an open ball in the Euclidean plane R2. This is the set of all x in R2 such that the Euclidean distance from x to C is strictly less than the radius. Now, I am ready to talk about the definition of an open set and a closed set in the Euclidean space Rn. Let omega be a subset of Rn. We say that omega is open if for any C in omega there is R greater than 0 such that the open ball with center at C and radius R is a subset of the set omega. The radius R depends on C in general, and a set F is said to be closed if its complement is open. Here is an example of an open set in the Euclidean plane R2. The set omega in this situation is a polygon without boundary. As you can see, for any C in this polygon, you can always find R greater than 0 such that the open ball with center at C and radius R is a subset of this polygon. Therefore, this set is an open set in R2. And here is another example. Let omega 1 be the open upper half of the Euclidean space, the Euclidean plane R2 given by this formula. Omega 1 is the set of all points in R2 such that the second component is positive. As you can see here, no matter what C we take in this upper half plane, we can always find a radius such that the open ball with that center and with that radius is a subset of the set omega 1. And therefore, omega 1 is an open set in the Euclidean plane R2. Here is an example of a closed set in the Euclidean plane R2. Let omega 2 be the closed lower half of the Euclidean plane given by this formula. This is the set of all points in R2 such that the second component is less than or equal to 0. We can see that the complement of omega 2 is omega 1, which is an open set in the Euclidean plane R2. Here, omega 1 is the set we considered in the previous example. Therefore, omega 2 is a closed set in the Euclidean plane R2. Finally, I am going to talk about some important properties of open sets in the Euclidean space Rn. The empty set and Rn itself are open in the Euclidean space Rn. If G alpha for alpha in I is an arbitrary collection of open sets in the Euclidean space Rn, then their union is also open in the Euclidean space Rn. If G1 and G2 are open in the Euclidean space Rn, then the intersection of G1 and G2 is also open in the Euclidean space Rn. Now, if we denote by tau the collection of all open sets in the Euclidean space Rn, then we have the following properties. First of all, the empty set is in tau and Rn is in tau. Based on the second property here, we see the following. If G alpha is in tau for all alpha in I, then the union of G alpha where alpha in I belongs to tau as well. This property tells us that tau is closed under arbitrary union. And the third property says that if G alpha is in tau and G2 is also in tau, then the intersection of G1 and G2 is in tau. And we say that tau is closed under the intersection of two sets. By induction, we can show that tau is also closed under the finite intersection. In the next video, I am going to talk about the definition of a topology on a set X. And as we will see, tau is a topology on Rn. And this is called the usual topology on Rn, or the topology induced by the Euclidean norm in Rn. Thank you for watching.